Okay, good morning. So today we will start our lecture 18. And we will talk about multiplicative questions and integral domains. So multiplicative questions in rings. Questions and integral domains. Okay, so we had quite a long time since the previous lecture, so let me start by recalling a definition. What will be a definition 1 for today? So we say, so let R be a ring. Let R be a ring. Then we say that R is a ring with unity. We say that R is a ring with unity. If there exists an element, exists an element which is commonly denoted as 1 in R, such that when multiplied by any other element, so if we look at 1 times A or A times 1, this is the same as A for all A in R. Okay. And we also say that R is a commutative ring. If the multiplication operation is commutative. In other words, AB equals BA for all AB in R. Okay, so today we will have a closer look at the second binary operation, which is multiplication. And what we will talk about is various, first of all, subring generated by unity, and also we'll talk about the so-called zero divisors. Okay, so let's start with a simple lemma as a warm-up, and the lemma will be formulated as follows. Lemma 1. When exists the unity 1 in R is unique. And the proof would be more or less identical to how we proved that the identity element in the group is unique. So we will suppose that there exist two elements. Suppose there exist two unity elements, 1 and let's say 1 prime in R. And because they're unity, this means that 1 times A equals A times 1 equals A for all A in R, and 1 prime times A equals A times 1 prime equals A for all A in R. Well, then let's look at their product. 1 times 1 prime, right? So we have condition star, and by condition star, we know that it must be equal to 1. On the other hand, by the condition double star, it must be equal to 1 prime. So these two elements must be the same. So 1 prime equals to 1. Okay. Now, lemma 2 would be the following. Again, R is a ring. Let R be a ring with unity such that this unity equals to 0. Well, then what we can say that R is a 0 ring. And R is a 0 ring. Okay, so there's actually no other non-trivial examples of ring with unity where the unity and the 0 would coincide. Okay, so similarly to how we defined generating sets for subgroups, we can define generating sets for subrings. Well, that will be our definition 2. So let R be a ring and S be a subset of R. Be a subset. And we say that a subring R prime in R prime in R is a subring generated by S if R prime is the smallest subring of R containing S. Yes. And here I want to make again this remark that we can talk about the smallest subring, talk about smallest subring because intersection of subrings is again a subring. Section section of subrings is again a subring. Okay. Now, basically, the R prime would consist of all finite, products and sums in the generators. So, R prime, lemma 2, lemma 3, R prime. Actually, I don't really want to go into too much details about it right now. So any questions so far? Any questions about our recap of the previous lecture or definition of a subring? Okay, so now let's have a closer look on the unital ring. So now let R be a ring with unity with unity 1R. And we can ask an immediate question. What is the subring? What is the subring generated by a singleton set which only contains unity? And it turns out that we can actually describe explicitly this subring, and that's what we will do in the following lemma. Turns out that can easily describe this subring, and okay. So in order to answer this question, we will look at the following. So that'll be lemma 3. And so here let R be a ring with two binary operations, plus and star be a ring with unity 1 in R. And in particular, what we know is that if we look at R as a set equipped with binary operation plus, it will be an abelian subgroup. So R plus is an abelian group, sorry, is an abelian group. So inside this abelian group, we can consider a subgroup H generated by unity of the ring. So let H be a subgroup of this abelian group. This abelian group generated by the unity. Generated by the unity. So then the claim is that in fact H is a subring. Then H is a subring of R plus star. Okay. Proof. So when we have a subset of a ring, and we want to prove that this subset is a ring, we need to prove two things. First of all, that it is closed under addition, and together with binary operation plus, it forms an abelian group, right? So need to prove that, first of all, H is closed under addition. So we can talk on the first place about the binary operation plus on H. And once we can talk about the binary operation plus, we need to prove that H plus is a group, is an abelian group. Abelian group. And finally, we need to prove that H is closed under multiplication. Right? And then all the kind of axioms of a ring would follow from the axioms of a ring for R. Okay, so now these two parts are true by construction of H. Of H. Remember that we defined this H as a subgroup of an abelian group generated by 1. So the only thing we really need to show, is that H is closed under multiplication here. Right. Okay. So as a set, H contains the following elements. So there's obviously 0, right? Which is an identity of this abelian group R plus. There is 1. There is 1 plus 1. There is 1 plus 1 plus 1 plus 1. And similarly, there is like minus 1 plus minus 1 plus minus 1, etc. Okay, so let's look what happens if we multiply any of the two elements. So for the case A, let's take an element which is just 1 added with itself n times. So this is n times. And let's multiply it by 1 added with itself m times. M times. Now we can use the distributive law, R3, to expand it as follows. Let me start on the next line. So by R3, this is the same as 1 times 1 plus 1 plus 1 plus 1 m times plus 1 times the same thing m times, and this is all repeated n times. This is all repeated. n times. So then applying R3 again to each of the summands, we would get that this is the same as 1 plus 1 plus 1. M times plus 1 plus 1 plus 1 times, etc. And altogether, this will be n times. And this, of course, is 1 added with itself, mn times. Recall that here, plus was the abstract operation plus in the ring R. Now the case B, which I, of course, won't write down, would be the following, that if you look at minus 1 n times oh, that's an operation star, to be clear. And if we multiply it by 1 plus 1 m times, then of course you will get minus 1 plus minus 1 mn times. So there's also cases C and D. Case C plus case D, which proved absolutely equivalently in absolutely equivalent fashion. So as a conclusion, we get that H is closed multiplication. It's closed under multiplication. So as a corollary, H is closed under multiplication and hence form a subring. Now this this subring give rise to the definition of a characteristic. So that will be our definition 3, I believe. So let R, actually let me move to the next slide, because this will be I can probably, so I won't have to squeeze it here. In the meantime, do you have any questions about this part with the subring generated by 1? Definition 3. I'll let R be a ring with unity, with unity 1 in R, and H be a subring generated by 1. Be a subring. Now, when H is finite, we say that the cardinality of H is the characteristic of a ring. We say that cardinality of H is a characteristic of a ring. And when H is infinite, we say that the ring is of the ring R is of characteristic 0. We say that the ring R is of characteristic 0. Zero. And actually more than that, kind of we can describe H up to isomorphism purely based on its cardinality. So we will have lemma 4, which tell us the following. So again, H is a subring generated by 1. So when cardinality is finite and equal to n, some number is finite, then this H must be isomorphic to the n as rings. And when H is when the cardinality of H is infinite, then H must be isomorphic to the ring of integers as rings. So in other words, in every ring with unity, there sits a very special subring, which is either the ring of integers or the ring of integers mod n. So let's look at examples. So any questions so far, by the way? Please ask questions. So let's start with kind of example 0. So let R be a ring of real numbers. Then this H generated by 1 is nothing but the ring of integers, right? Which is a subring of real numbers. So in this case, characteristic is so the ring of real numbers is a ring of characteristic 0. Let's look at some examples of rings of positive characteristic. Example 1. So let's take R to be a 2x2 matrices. 2x2 matrices with entries in Z3. So recall that if K is a ring, then so is matrices, and by n matrices with enters in K. Okay, so this is the ring. So the elements of this rings are 2 by 2 matrices where we have entries to be elements of Z3. Okay, so this ring is unital. So this ring has a unity. Let's denote it by, I don't know, solid 1. Solid 1, and this is 2 by 2 matrix with ones on the diagonal, right? Mat2 of Z3. Okay, so what is H? So as a set, H will be the following thing. So let's look at a subgroup of the additive group generated by this identity matrix. Well, obviously it will contain 0 matrix, right? It will contain this identity matrix itself. It will contain matrix with kind of 2 on the diagonal, and that will be it, right? Oh. So this is the identity matrix itself. This is the identity matrix plus the identity matrix. That's 0. Okay, so as a ring, this H will be isomorphic to Z3 as rings. Because if you multiply diagonal matrix by another diagonal matrix, what happens is just elements on the diagonal multiply, right? So you will get precisely the same addition and multiplication as in the ring of integers mod 3. So in this case, so the characteristic of mod 2 of Z3 is 3. And that's actually the general thing. If you have kind of a ring K with characteristic n, then matrices over K, no matter which size, the ring of matrices will have the same characteristic. So that's this example actually generalizes. Okay, so any questions so far? Okay, so here let me make a remark, which might be a subtle point when you first look at it. So again, let R be a ring with unity, 1 in R. So we can denote two as being 1 plus 1, right? 3 as being 1 plus 1 plus 1, minus 2 as minus 1 plus minus 1, etc. And this notation will be consistent. Notation is consistent let's say that with powers of elements in the abelian group R plus. Abelian group R plus. In other words, if you look at this n and multiply it by an element x, then by the distributive property R3, that will be the same as x plus x n times when n is greater than 0 times when n is greater than 0, 0 when n equals than 0, and minus x plus minus x, absolute value of n times when n is less than 0. So in other words, nx equals to n multiplied by x for all x in R. Just to bring your attention to the fact that kind of in this last formula, this is multiplication in R. Multiplication in R, and this is nth power of x, nth power of x in abelian group R with the binary operation plus. So there's two different operations, but of course notations are kind of designed to be consistent with that. Okay. So we kind of when we looked at the rings with unity, this resembled us the definition of a group, except for the fact that not every element might have multiplicative inverse. So now let's talk about multiplicative inverses. So what about multiplicative inverses? Well, of course, not every element would have multiplicative inverse, but when it has a multiplicative inverse, we will call it a unit. So that will be our definition 4. So let R be a non-zero, and like we proved in the beginning of the lecture, this means that unit is not equal to 0. A ring with unity, one in R. Then we say that x, an element x of the ring R, is a unit if there exists an element y in R, which is a multiplicative inverse of x. So in other words, that x times y equals y times x equals to 1. Now, if every non-zero element of R non-zero element of R. Oh, sorry. Non-zero element of R is a unit. We say that R is a division ring. Say that R is a division ring. Or skew field. Or skew field. That's just a synonym of that, sometimes used. And finally, just a common notation, the set of all units in R is denoted by R cross. So this is a subset of all elements which have multiplicative inverses. Okay, so here it's an important remark. Unfortunately, unit sounds a lot like unity, but those are different notions, as you might see. So remark, do not confuse unit with unity. Do not confuse unit with unity. So always, please always pay attention to that. I cannot say that I always pronounce it correctly by myself. So that's kind of quite misleading that they sound really similar, unit and unity. So unity is the unique element which, when multiplied by every element, gives back this element x. However, unit is just element which have a multiplicative inverse. So please keep that in mind. Okay, so now let's look at example, a couple of examples. So the basic example we would want to look at would be the ring of integers, right? So Z is a ring with unity, that's denoted as 1 in Z. So what are the units? Units of Z. So what is the set of units? And that's the question to the audience. What is the set of integers which have multiplicative inverse? Okay, so this is 1 and minus 1. Well, this means that Z is not a division ring. So not every non-zero element has multiplicative inverse. Inverse. So Z is not a division ring. And I believe this was example 2. Okay, so now let's kind of just mention the standard examples of division ring. And that will be example 3. So if we look at the ring of rationals, the ring of reals, the ring of complex numbers, and the ring of quaternions, they are all division rings. Are all division rings. So you would have that the multiplicative subset of Q is basically Q minus 0. So every non-zero element has inverse. Then the multiplicative subset of C is C minus 0. And what is most interesting, and we will elaborate about this a little bit more, is that all the subset of elements in quaternions which have multiplicative inverse is also all non-zero quaternions. So for the first 3 examples, it's kind of obvious. Let me look at quaternions. So if you look at the following element, so suppose we have A plus B times I plus C times J plus D times K, then it will have a multiplicative inverse, which can be calculated as follows. So this will be 1 over A squared plus B squared plus C squared plus D squared multiplied by A minus BI minus CJ minus DK. Formula is very similar to the formula for the inverse of a complex number, for the multiplicative inverse of a complex number. But recall that quaternions is actually an example of a non-commutative ring. So this is a beautiful example of a non-commutative division ring. So H is an example of a non-commutative division ring. Non-commutative division ring. Okay. And finally, let's look at example 4. So here the ring will be the ring of n by n matrices with real entries. So is a ring with unity. Then if we look at n by n matrices with non-zero determinant, and this subset is actually GL and R. That will be precisely the subset of units and not n R. Collection of units. Now, in example 2 and example 4, you might notice certain pattern. That this thing is actually a group. And is isomorphic to Z2 as group. Now this thing is a group as well. And this is not a coincidence, of course. This is not a coincidence. In fact, the following is true. So let's say that this will be theorem 1. Let R be a ring with unity. One in R, and R cross be its multiplicative subset. Be the subset of units in R. And to be precise, let me kind of denote the binary operation of R by plus and star. Then what is true? Then R, that this subset R cross with a binary operation multiplication is a group. And the proof of this theorem would go as follows. So first we need to show that R cross is closed under multiplication. In R. Well, indeed, suppose x, y are invertible. Well, then so is x star y. So here just take x star y inverse to be inverse of x multiplied by the inverse of y multiplied by the inverse of x. Okay, so the binary operation star from R cross R cross to R cross is well defined. Okay, so that's the first part. Now the second part is that unity 1 over ring belongs to this is a unit. So and it serves as an identity. Element of a group R cross with the binary operation star. And indeed, if you look at 1 times x, this is the same as x star 1, the same as x for all x in R cross, right? And finally, the existence of inverses is built into this definition. Note that if X is a unit, and so is X inverse. And the moral of this theorem is that with every with every unital ring, we can unital ring R, we can associate the group of units, R cross in the binary operation star. So R itself, with respect to the addition, forms an abelian group, but there's actually a different subset, which is R cross, which forms a group with respect to the binary operation star. So any questions about this? Okay, so to conclude our discussion about this multiplicative inverses, let me introduce the definition. Let me introduce
Professor?
Yes?
I had a quick clarifying question about the previous theorem that we had. So when we say that R cross with star is now a group, if we added the addition operation, it's also a substring, right? Or subring, right?
Excellent question. Now, R cross is not closed with respect to the addition operation in most cases. Oh. So let's go back to our example here, right? Let's go back to our example here of the subset of units in the ring of integers. So note that Z cross is not closed under binary operation plus. So consider 1 plus 1, right? It's 2, and it doesn't belong to Z cross.
Okay.
And actually, in every ring, that would be true, right? So what suppose you have a non-zero ring. Suppose you have a non-zero ring. In general, if you have zero ring R, then what do you, with unital, then what you can do, you can take 1 and you can add -1. So this obviously belongs to the multiplicative group. This also belongs to multiplicative group because it must be its own inverse. And the 0, which is not an R. So this is, you cannot make, in other words, you cannot make the set of units to be even closed with respect to the binary operation plus.
Mhm.
So that's, does it clarify the question?
Yes, it does.
Okay.
Thank you.
Thank you for asking. That's a great point to make here. Okay, so let's conclude with giving a definition of a field and strictly skew field. So a field is a commutative division ring. Is a commutative division ring. So a non-commutative division ring is called strictly skew field. Non-commutative division ring is called strictly skew field. It's called strictly skew field. Now, the second part of this definition is, of course, kind of not the best piece of terminology. So okay, so and here note that Q, R, C are fields, while H is a strictly skew field. Skew field. Now, this fields is actually a very special type of a ring for which you can prove many interesting properties. And they studied a lot in the second course of abstract algebra, and they are studied a lot in the graduate versions of abstract algebra. But just here we'll just point it out that from the fact that every non-zero element has a multiplicative inverse, you can actually squeeze a lot. So that's just okay. So this brings us to the next question. What is there anything interesting? Is there anything interesting that can happen when R is a unital ring which is not a division ring? It's not a division ring. And you see here kind of our basic intuition is, of course, comes with experience with, rationals, real or complex numbers. And the case when not every non-zero element has a multiplicative inverse is might appear somewhat counterintuitive at first. And the first kind of surprising things that can happen here is the phenomenon of zero divisors. Divisors of 0. So let me start by looking at the motivating example. Motivating example. So let's look at the ring of integers modulo 6. Ring of integer modulo 6 with operation plus and times, the standard operation you would think of. And let's look at the product of two residue classes mod 6. So let's look at 2 and multiply it by 3. So what you will discover, what will be the result of this multiplication in Z6?
The 0 group?
Yes, that's right. Great. So what we will get is the 0 element. So you can take two non-zero element, you can multiply them and get 0. And this is where our intuition actually breaks, kind of our intuition coming from high school algebra about, will break here, because in particular, right cancellation laws doesn't hold here. Cancellation laws don't hold here. Don't hold in this ring. So let's look, for example, at if we take 4 and multiply it by 3, right? That's 0, and that's the same as 0 multiplied by 3. But from here, it doesn't follow. Well, okay, let me write it differently. But 4 is not the same as 0. So when every non-zero element had multiplicative inverse, we get used to think that the right cancellation laws hold. And that's precisely because we kind of taken this multiplicative inverse and multiplied, the equation on both sides by it. But when the elements are not invertible, interesting things start happening. And okay, so you might, from this example, first of all, any questions? Any questions about what I just considered on the whiteboard?
Just a clarification then.
Oh,
If you say
sorry.
right cancellation laws don't hold, then that implies that the left cancellation laws don't hold either. Because if you just
Yes.
flip the two.
Yes, and that will be a theorem. Thanks for introducing that. Okay, so from this example, you might get you might kind of get the impression that you haven't seen examples of rings with a division ring, with divisors of zeros, and that's actually not true. So let me introduce a couple of examples which suggest that this is something that was always just around the corner. So let's look at example. Oh, I already lost track of what number is. Probably it's 6. Example 6. So recall that. So let x be an interval from 0 to 1, and then the collection of functions f. So those are all functions from x to reals is a ring. Okay, so now let's look at two functions. Now let's look at two functions. So let's say, okay, so this will be 1, this will be 0. And one function will be 0 almost everywhere except for, small hill here. So this will be f of x. And another function will be 0 almost everywhere, but will have hill at a different place. Let's say this is g of x. So note that f is not 0 and g is not 0 as elements of a ring F, right? So these are not 0 elements. The 0 element of calligraphic F is 0 function, which is 0 everywhere. However, Fg equals 0. And F, if you take the product of these two functions, you'll get a function which is 0 identically. And okay, so any questions about this example? Okay, so in example 7, let's look at our favorite linear algebra and consider the following ring, which will be, let's say, 2 by 2 matrices over reals. Then let's look at the following two elements. So the first element will be a matrix 0, 1, 0, 0. The second element will be a matrix 0, 0, 1, 0. And the third element will be a matrix 1, 0, 0, 0. So none of them are 0. None of them are 0 None of them are 0 matrices. What do we have? Well, let's look, for example, at M1, M2. Okay, so on the first entry, we will get 1. On the second entry, we will get 0. On the third entry, we will get 0. And on the last entry, we will get 0, right? Well, that's not 0. Nothing kind of too unexpected. But now let's look at M2 and 1. So 0, 0 times 0, 0, that's 0. 0, 0 times 1, 0, that's 0. 1, 0. Oh, this one is a bad example, by the way. I started with the wrong kind of. So 1, 0, that's 0, 0, 1. Okay, so disregard this pair. Nothing cool. Now let's look at M1, M3. So for M1, M3, we'll get a 0 matrix, right? Because no matter how you multiply, you'll always get 0 matrix. Wait a second. Oh goodness. I screwed this one up. This is 0. The first entry is 0. The second is 0. This is 0. And the last is 0. Oh, no, good. Okay. Let's look at M3 and 1. So if we look at M3 and 1, okay, so the first kind of element is 0. The second element is 1. Then the other two are zeros. So when the product of two elements is 0, we say that these elements are 0 divisors. And here you can note that kind of left 0 divisors is not the same as right 0 divisors. So let me put this definition. And that will be our last definition for today. So if AB belongs to R such that A is non-zero and B is non-zero, but AB equals to 0, we say that A and B are 0 divisors. A and B are 0 divisors of R. More precisely, A is a left 0 divisor, 0 divisor if there exists B in R such that B not equal to 0, but AB equals to 0. Similarly, B is a right 0 divisor, 0 divisor there if there exists non-zero A in R, such that A is non-zero, but AB equals to 0. So when a ring is commutative, it doesn't matter. When R is commutative, then left and right 0 divisors coincide. There's coincide, of course. Okay, so that would be the great point to stop this lecture. And next time we will talk about integral domains and Fermat and Euler theorems. So please ask questions if you have.
Do left
Yes?
and right divisors coincide when R is not commutative?
Well, that's a great question. So if we kind of look at slightly more sophisticated examples, we will find kind of left 0 divisors which are not right 0 divisors. So I'll probably put some kind of optional exercise to the next homework about this. Thanks for bringing this up. More questions? Okay, so then I'll stop the session with the lecture, and I will continue with the same meeting ID for the office hours in just a few minutes. Thanks.